Okay, continuing our further mathematics series in calculus, we're now going to move on to differentiation of the inverse trigonometric functions. So there are three trig functions that you need to be able to find the differential of the inverse for. They are the arcsine function, the arccos function, and the arctan function. And then, just for a bit of fun, we're also going to look at the differential of the arcsec function, although that isn't really one that's on the course. But just a bit of fun, just a bit of wider reading. So these three, the differentials for them are given in the formula booklet for further maths MEI. However, you also do need to be able to prove them. But if you're not asked to prove them, you can just use them. You can state them and use them. Okay, first of all, let's look at the differential of y equals arcsine x. Okay, so what I'm going to do is I'm going to take the sine of both sides of this graph, and I'm going to end up with the sine of y is equal to x. That's okay to do. It's a little bit tricky to go the other way. You're going to arcsine both sides because of the limited domain on the arcsine function, but going the other way is fine. And I just want to kind of bear in mind that this function, the arcsine function that is, looks like this in its entirety. That's the whole graph. It's not a piece of the graph, that is the whole graph. It stops at this point and finishes at this point. Between x is minus 1 and x is 1. We should note that from A level. But what I want to point out at this point is that the gradient along the whole of that curve is a positive gradient. So y primed is going to be positive for every x value in the domain, which is between minus 1 and 1. That's going to be important a little bit later. Okay, so what I'm going to do is I'm going to differentiate this implicitly. So that's going to give me the cosine of y times y prime is equal to 1. So that's taking the derivative with respect to x. I'm going to divide both sides by the cosine of y. So I'm going to end up with y prime is equal to 1 over cos y, which is a correct derivative, but I started with y as a function of x. So what I really want is dy by dx to also be a function of x, whereas at the moment it's a function of y. So I'm going to employ a trigonometric identity to replace the cos with a sine. And that's going to be equal to the square root of 1 minus sine squared of y under the number 1. So that is the cosine. And I'm taking the positive square root because y primed is positive. Okay, so this is where this comes in. All right, so I'll take the positive square root of that trig identity because I want the derivative to be positive everywhere. How does that help us? Well, sine y is, by definition, x. So I can replace this sine squared y with x squared, and that gives me the square root of 1 minus x squared under the number 1. This is the derivative of arcsine. Okay, that is given to you in the formula booklet, but you do need to know how to do that, and you do need to justify taking the positive root. Okay, second one, arc cosine. This is very, very, very similar. Again, we take the cosine of both sides, so we're going to get cos of y times y primed is equal to 1. Okay, so I've taken the cosine and then differentiated. Oh, no. That would be minus sine if I differentiated. Start again. Minus sine of y times y primed equals 1. So that's me taking the cosine of both sides and then differentiating implicitly. That means then that y prime is negative 1 divided by sine of y. And for the arc cos curve, what I want to point out is that the gradient is actually negative across the whole domain. This is the graph of the Arccos graph, which again is one that you should be familiar with from A-level mathematics. And the gradient between there and there, which is the whole of the graph, is always negative. So I'm looking for a negative gradient. Again, I can use that same trig identity to get 1 minus cos squared of y under the square root, all under number 1. And now I point out that cos y was actually x. That was the step up here, which I should have done really. Cos y is x, so that is going to be the negative 1 divided by the square root of 1 minus x squared. And that's the derivative of the Arccos function. Okay, one more. I'll say one more of the ones you need to know. We'll also do Arctan. So this one, we'll also do Arcsec. We're going to do Arctan. So we're going to end up with the tan of y is equal to x. That's taking the tan function of both sides. Differentiate implicitly. Tan y differentiates to sec squared y times y prime. And the x differentiates to the number 1. And that tells us that y prime is equal to 1 over sec squared of y, which, yes, I fully appreciate that that is cos squared. However, we are going to want to replace the sec squared with a tan so that we can put x back in. So I'm going to leave it as 1 over sec squared. We know that 1 plus tan squared is sec squared, so I can replace the sec squared with 1 plus tan squared using a trig identity from A-level mathematics. Still under the number 1. And that helps because tan of y is x. So that is actually 1 plus x squared under the number 1. Okay, so no surds. It's just the most simple quadratic, really, in the denominator. Okay, so those are the 3 that you most certainly need to know how to do, and those are the 3 that are given in the formula booklet. So if you need to use any of those, then you can just state them. And then for a bit of fun, we're going to do the arcsec function as well. So the arcsec, same as before, what we're going to do here is we're going to take the secant of both sides. So that's going to be sec of y is equal to x. Differentiate. The differential of sec, you know what? Let's not differentiate sec. Let's reciprocate this. And let's say the cosine of y is equal to 1 over x. I think this might be slightly easier to do. And now differentiate implicitly. We get minus sine y times y prime is going to equal negative 1 over x squared. Now I can divide by the sine y, and then I just need to make sine y so I need to make sec y within that sine function, so I can replace that with an x. So that's going to give me y prime is going to be equal to x squared sine y, all under the number 1. The negatives have cancelled. Okay. Right. Sec y equals x, and I want sine y. So what I'm going to do is just going to create a little triangle over here, which defines sec y as being x. So there's my y, and the secant is 1 over the cosine, and the cosine is adjacent over hypotenuse, so therefore this must be the hypotenuse over the adjacent. So therefore, if I put an x there and a 1 there, this triangle represents the sec of y is equal to x, because the cos of y is equal to 1 over x. Okay. Adjacent over hypotenuse. Now I can use Pythagoras to give me that this must be the square root of x squared minus 1. And now I can pull out the sine because I've got x squared minus 1. So therefore, sine of y, which is opposite over hypotenuse, is going to be the square root of x squared minus 1, all divided by x. Now you can obtain that in different ways. You don't have to use this triangle. You can get to it just using the trig identities if you wish to. But personally, I quite like that. Draw a little triangle, apply Pythagoras, and then we can extract the trig function that we want. That can be used in quite a lot of different ways. Okay, so now if I apply that into here, I'll end up with dy by dx is going to be equal to 1 divided by x squared times sine y. So I'm going to reciprocate the sine. I'm going to get x on the top, the x squared on the bottom, it's still there. And then I've got the third on the bottom, x squared minus 1. And then I can cancel an x top and bottom to give me x into the square root of x squared minus 1, all under the number 1. Okay. At this point, I'm just going to be really careful just to make sure that this square root here should be the positive square root. And let's have a look at the graph of the function. Now, this is not something you need to know for the A-level course. It's just of interest. But the sec curve, the full sec curve, looks a little bit like this. It does repeat every pi, just like the cosine curve does. And if you want to find the inverse function, the arcsec function of this, then we're going to restrict the domain to be between 0, which is here, and pi, which is here. Just like we do with the cosine function. We restrict between 0 and pi. So, how does that help? Well, this makes the graph look like this. And you get a little vertical asymptote here, at pi, and then that's going to come in and stop there. Sorry, pi on 2, and that's going to stop there at pi. Okay, so that's the sec function, restricted to be between minus pi, 0 and pi, and then to find the inverse, we just reflect that in the line y equals x, as you would for any other inverse. So the inverse function looks like this. Okay, no negative outputs, so therefore no negative inputs, so just the x. We've got negative and positive outputs, so we're going to have negative and positive inputs. And we're going to end up with this 1 here on my vertical axis is going to become a 1 on the horizontal axis. And it's going to shoot off that way. We're going to get an asymptote here. Okay, so that vertical asymptote reflected in y equals x to become a horizontal asymptote. And then we're going to end up with the curve coming in from that side and stopping there. Okay. So that's the entire curve. That's the inverse sec curve, or arcsec. And what I'd like to notice is that everywhere on that curve, the gradient is positive. Positive, 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 positive. The problem is what we've got currently is we've got a positive number divided by a number which could be positive or negative, times by a positive number. That's always positive. So what I should do is I should make this always positive. And there's 2 different ways you can do that. Number 1, we can pop little modular signs either side, like that. That now works. Or, if you don't like the modular sign in that function, what we can do is we can square it and then bring it into the square root. So we end up with dy by dx is equal to the square root of x squared. That makes it positive. If it was negative, times x squared minus 1 square rooted, all under the number 1. So I'm forcing out that x to be a positive, and then I can bring that into the square root symbol, and that gives me x to the 4. Subtract x squared under the number 1, and that's the derivative. Okay. As I said, that's not one that we need for this course. I just think that's vaguely interesting, so I thought I would include it. Okay, right, let's get rid of that. This is what's given in the MEI formula booklet. Other examples might be the same, but I'm unfamiliar with other examples. We have an f of x column. This is in the calculus section on the core pure. And then you've got arcsine, arccos, and arctan. And then we have the derivatives of those as being defined as these 3. Okay, so that is a complete snippet of what we are given in the formula booklet. So you can just state and use them without proof, unless you are asked to prove one of them, in which case, obviously, you need to do what we just did. Okay. So we can apply that, or those formula that are given, to differentiate more complicated functions. It's exactly what we'd be expected to do in an exam setting. So part A, or part I, what I'm going to do is I'm going to use the chain rule. Okay, right back to regular A-level maths. The chain rule still applies. I'm going to say this is the arcsine of u, and I'm going to say u is equal to x squared subtract 1. Differential of that, well, we can state it because it's in the formula booklet. So that is the square root of 1 minus u squared under the number 1. And this, well, that's just really easy maths now. It's just 2x. So now we can replace the u squared again with our x squared minus 1, because that's what u is. And then times it by 2x. So the derivative then, d by dx of arcsine of x squared minus 1 is equal to the square root of 1 minus u, and u was x squared minus 1, but that was u squared. That's in the square root. And then we're going to times that by 2x, by the chain rule. So that is the derivative. We can tidy that up a little bit if we want to. You don't have to. But if I take this bracket here and square it, the ones actually cancel. And I can combine some things together. And I end up with the square root of 2x squared minus x to the 4. All under 2x. That's the answer. It is tempting to pull an x squared out from the square root and cancel it with the top, but then that would not be correct because the gradient would always be positive, whereas actually we want the gradient to be negative sometimes, I think. Probably should have checked that before the video. Anyway, in fact, let's check it now. Let's have a look. Let's have a look at this graph. So let's delete those. Right, let's do the inverse sine of x squared minus 1. And let's have a look at that. There we go. Yeah, so we want the gradient to be negative on the left and the gradient to be positive on the right. So therefore, we cannot cancel an x squared from the denominator with an x in the numerator because we want that negative gradient when x is negative. So we just leave it alone. Okay. All right. Question 2. This one here, this one's going to involve a product. We've got 4x cubed multiplied by arctan of 8x plus 3. So if you need to write the u and the v down, then of course you do. That's fine. I'm not going to bother. I'm just going to say d by dx of 4x cubed arctan of 8x plus 3 is equal to, that times the differential of this, so that's going to be 12x squared times arctan of 8x plus 3 plus the 4x cubed times the differential of this. That's going to be 4x cubed multiplied by the differential of the arctan function, which is 1 over 1 plus the contents of the arctan function squared, which is 8x, 8x plus 3. But then by the chain rule, I need to times that by 8. Okay, times it by the derivative of that. Okay, I can definitely do a little bit of tidying up there. So the 12x squared arctan 8x plus 3, I'm just going to leave alone. So 12x squared times arctan of 8x plus 3 can just sit there. I'm going to get a 4 times an 8, which is a 32. Can I cancel anything in the bottom? I'm going to get a 64x squared, so that's even. I'm going to get 48x, 2 of those, so that's even. And then I'm going to get a 9 plus 1, I'm going to get a 10. That's even, but only divides by 2 once. So I can divide one of the 2's top and bottom. So I'm going to get 16x x cubed in the numerator. And then in the denominator, I'm going to get 8x times 8x is 64, but I have halved it, so 32x squared. 3 times 8 times 2, but then halved, is just the 24x. And then I've got the 9 plus the 1 is 10, but I've halved it, so plus 5. And there's no other common factors top and bottom there. So that's it. Okay. And my final question was to differentiate this thing, which is a fraction. And I've got a variable on the top and a variable on the bottom. So therefore I should use the quotient rule. So the differential of Arcsin divided by Arccos I'm going to set u to equal Arcsin. Using the formula booklet, u primed is, I've just covered up the formulas, 1 minus x squared to the negative a half. V is the denominator, so that's the arc cosine. And then v primed is the negative of that, so it's negative 1 minus x squared to the minus a half, again taken from the formula booklet. I can now use those for the quotient rule formula. So d is going to equal vu primed, so it's that times that. So it's going to be the arc cosine of x divided by the square root of 1 minus x squared. Subtract uv primed, but that's already negative, so subtract the negative is a positive. And that's arc sine of x divided by the square root of 1 minus x squared. And then that's all going to be divided by v squared, which is arc cos of x squared. Arc cos of x squared. Don't be tempted to put arc cos squared of x. That's not actually a thing. That's not notation that we use. We've got fractions and fractions, so let's just tidy that up, and then we can just leave the answer as the arc cos of x plus the arc sine of x, all divided by the square root of 1 minus x squared into arc cos of x squared. That's it. Okay, so that's all I wanted to do this video. Those are the derivatives of the inverse trig functions, which you need to know and work with. In the next video, we're going to use those in reverse to allow us to do some more complicated integrations. Thanks so much for watching. Please drop any comments if you have any questions.